Okay, so now we're stepping back into doing mostly algorithms again. This P versus NP will still kind of be floating in the air and we'll occasionally stumble into problems that aren't easy again. But as far as like the main part of that story, we've already covered that main part of P versus NP. And I think that's actually kind of the, I don't know, intellectual high water of the class in some ways. And in fact, I tried to do it a little earlier in the semester so that you have much more time to process. A lot of people do it at the end. I used to do that too. But you kind of like cram it at the end, and then on the final exam, like no one does anything correctly related to it. And I think part of it is just it takes some time to let it soak in. So that's why we try to put it a little bit earlier. So today we're going to do something called spanning trees, but it's sort of kicking off a leg of, yeah, it's going to be kind of graph algorithm-y, but it's going to be a little bit more emphasis on structure. I'll explain, maybe they're more properly in combinatorial optimization to some extent. But in any case, it's usually fun. It feels like after kind of slogging through this complexity, we're back to kind of solving things algorithmically a lot. And then it's all kind of downhill from here. So, all right, so here's sort of the basic original, I think, motivation for this problem. So I guess back when they invented electricity, so this might be like the 1890s, 1880s. Anyone knows? Probably after Civil War. But anyway, they have this basic question of like, well, I need to connect all the houses in the town with wiring so that they can get electricity. And they want to use the minimum total amount of copper or something, right? So here I've drawn a few houses and I've drawn some edges in between them. And your goal is to come up with a subset of edges that connects all the houses together. But you want to use like the minimum amount of edge length. So just assume like the edge length is proportional to whatever is drawn. Okay. And so you're trying to find the minimum kind of amount needed to connect this graph together. Okay. So maybe I'll let you look at it and then I'll just ask you to kind of shout out pairs of edges and I'll fill in that and we'll gradually connect the graph as cheaply as possible. Maybe it's like kind of hard to remember what you took or something, but how about this? You just like shout out some edges and I'll start coloring it in until it gets connected and we'll see if it looks pretty good afterwards. So any edges I should take?
1, 3.
1 and 3. Okay, there's 1.
3, 6.
3, 6, Mafia. Okay.
6, 8.
6, 8.
6, 7.
6, 7. You could have said 7, 6.
That's true.
Okay. 4, 2. 8, 9. And 8, 4. Okay. So seems reasonable. I look at it. I'm not sure if I can improve it. Maybe there's a little bit of ambiguity about which one's shorter between these two. It's not too important. Oh, we're not done. Okay, sorry. Not a very good teacher. Okay, what guided you? What motivated some of the choices? Like, why did you choose 1, 3 first? There's no like right or wrong answer. I'm just like kind of curious what the thought process was. Yeah.
I was not the one who suggested the edge, but it's the like you're gonna have to connect to one at some point. It's the shortest outgoing edge of one.
Yeah, that seems a little bit natural, right? You're gonna have to take at least one edge, leaving one to connect to someone else. Why not take the shortest? Yeah, well, and in general, like what other ideas went through your mind? Why various other? Is that what you did everywhere? Yeah.
I was thinking more like Kruskal's algorithm, where you have to like sort that by from least to greatest, and you get from the least. That's why you get the least.
Yeah, okay. These are algorithms that are known. But okay, so you're suggesting, in general, let me just keep trying to take the smallest edge until they all get connected, which wasn't the exact order we went in, but that seems like reasonable, like some kind of greedy solution, trying to take as few as possible. Okay, whatever. So that's just some illustrative example. Maybe let me make three simple observations. I forget what order they're in, so we'll see. All right, first observation. There's no reason to have a cycle in your solution, right? Because a cycle from a connectivity standpoint represents some redundancy. You remove that edge from the cycle, everything still remains connected, right? So there's no reason to have a cycle. So it seems like we never, once we filled out a full tree, we just all seem to stop and recognize this. Another observation is that it seemed natural to take short wires. We haven't really proven that always works, but it seemed natural to at least always gravitate towards the shorter wires. And what comes next? Yeah, so here's maybe something interesting. I don't know if it's interesting. But if I look at any wire that I'm not using, right, like this one, you can ask yourself, like, why didn't I take it? And then you can see, I already have these connected. And there's always like some path connecting it. And this path seems like, maybe one thing to point out, even that edge, which is fairly big, so obviously it seems obvious you wouldn't want to take it. I should note that like the path connecting these endpoints is longer than that single edge, right? Although that's not really the question you're interested in, because your question is bumping out one of those wires to replace it. Just some observations to kind of get the juices flowing. Okay, so that's the kind of form of a problem that we're going to work up to today. So at some level today, compared to normal, we're going to just do a lot of observations that take place in graphs. And once you have all these observations, the algorithm part is actually not that hard. There's often many different algorithms that can accomplish the same thing. But it's more about like putting some observations together. It's not necessarily going to be a proof by induction like before. But you learn something about the graph, you could say something precise and concrete about the graph. And once you understand the structure of your problem, the algorithm is easy. And the next couple of chapters are also going to kind of have this feel. Okay, so there's going to be emphasis on kind of the structure of the problem. That seems ambiguous, but hopefully some examples will kind of elucidate that. So there's going to be a lot of definitions in this one. So, first, a circuit. I'm going to define a circuit as a walk that starts and ends at the same vertex. The only difference, and you're allowed to even revisit a vertex, like you can have like a figure 8. That's kind of okay. Okay, so maybe a cycle is another word for this. And our other vocab word, which of course is a forest. A forest is a set of edges that has no circuits or no cycles. Okay, circuits, cycles, I think I'll use them synonymously. But this is a forest, with multiple components. If there was only one component, and these are all connected together like this or something, then I would have a tree. Okay? You already know this, forest, tree, things like this. Nothing special. Okay, but we're just going to keep massaging these definitions. Okay? All right, so I said the lecture was about something called spanning trees. So span. So let's say I have a set of edges S in red and some other edge E. I'll say that S spans E if it already connects the endpoints of E. Okay, so it sort of like captures, when we're focusing on connectivity, it sort of captures whatever E has to offer. Okay, so that's called spanning. And what else is next? Okay, some notation, I can have some set of edges. I'll say the span of S is all the edges that it already spans. That includes S itself. And then finally, I'll say S is spanning if it spans every edge. Okay, these are very boring definitions, but it's good to establish this. Okay, anything down here? Nothing down here. Okay. All right, so with those definitions in place, what's a forest, what's spanning, we're going to look at two problems. So the first one, you're probably more natural, and that is, I want to find a forest in the graph with as many edges as possible. So my goal is to take as many edges as possible, but I'm limited. I'm limited because I'm not allowed to create any cycles or circuits. That's the definition of a forest. Okay? And the other problem, maybe a little more unusual, is called a minimum spanning set. So my goal is to take a minimum set of edges that spans every edge in the graph. Okay, so it should somewhat minimal redundancy with respect to connectivity. And those are like the two problems we're going to focus on. Okay, and I want to first point out one difference in their character. So I think it's this maximum versus minimum. In one, I'm trying to take as many edges as possible. And I have some like constraints that said you can't take more edges, right? Because if you did, you'll generate this cycle. If you took that edge, you'll generate that cycle. Okay. Another way to think about it is like for any cycle in the graph, I can take out most all but one of the edges. I can't take all of them, right? So these are like it's exponentially many, but a bunch of individual upper bounds. Here's a cycle of 10 edges, you can only take 9. Here's a cycle of 20 edges, you can only take 19. Okay? This is sometimes called a packing problem because they're like suitcases you're stuffing in. There's some limited amount of space. You know, each of these constraints is like another dimension. So like n dimension, gazillion dimensional packing problem. But it's packing, you're trying to stuff in as much as possible, and there's some limits to what you can fit in. The other kind of problem is kind of called a covering problem. Here it's maybe a little bit more abstract, right? But I'm saying, look, if I want to span this edge, I need to take enough edges that its endpoints are already connected. Okay, so every edge is like some kind of requirement. You need to take enough edges to cover this edge. You need to take enough edges to cover that edge, right? So you're trying to get rid of as many edges as possible. But there's these spanning requirements that limit how many edges you can drop. I want to drop another edge, but then this edge won't be spanned anymore. Okay, so that's a covering problem. You know, you might start with all the edges, but you're trying to get rid of as many as possible, and you're limited. They're both kind of monotonic, but they're going in opposite directions. Okay? So covering requirements, you're going to get as few as possible. Packing requirements, you're trying to take as much as possible. Okay, so good. All right, and actually one really important thing, right now they look like different problems, but we're going to see how they're connected, and that's almost like the real theme of this lecture. Okay, so maybe I'll start right here. Okay, so for simplicity, I'll say the graph is connected. Otherwise, you can kind of look at each component separately. And what we're going to do again is we're going to analyze these two problems jointly, right? They're both kind of natural problems. Give me a maximum size forest, give me kind of a minimal spanning set of edges, okay? And it's only going to be by analyzing them both jointly that we'll be able to say something very strong about optimality and algorithms and things like this. That's okay. So let's start here. Okay, so let's say I have a forest and I have a spanning set of edges, and it's a connected graph. It says, first, any forest can have at most n minus 1 edges, and that any spanning set of edges has at least n minus 1 edges. Okay? And almost a more interesting thing is that this also implies that any spanning set of edges has at least as many edges as any forest. Okay? All right, so let's see. Yeah, so we can focus on just one of these sides at a time, and then we'll do ideas for each one. So I left this blank. I didn't leave it blank. Okay, so let's focus on, let's say the first, we'll do one inequality at a time. So, all right, so this claim is that any forest has at most n minus 1 edges, which maybe seems completely intuitive to you. So I guess now the exercise is, how do I articulate this? How can I maybe get this down crisply? Because you're probably thinking, oh yeah, a tree on n edges has n minus 1 edges, or n vertices at n minus 1 edges or something, right? So yeah, okay, you kind of know the answer, or you know that this is true. So maybe the question becomes, how would I be able to actually articulate this? There's probably many different ways to do it. Of course, I have one way that's loaded up. Yeah. And what? Yeah, but it's, yeah, if you connect them, you might need to use n minus 1. Well, first of all, that's need to, so that says there should be at least n minus 1. And then the other is like, that feels a little bit close to what the question asks and almost restating the question, right? So I think we want to just go even more grungy, slowly, a little more first principle-y. Yeah.
I think starting with your base case with just 2 nodes in your forest, you have 1 edge, right? And then for every edge you add after it, you can either connect it to a node in the forest and add it to a node, which adds 1 node and 1 edge. Or if you connect it to 2 nodes that are already inside the forest, then you would have a cycle. So for like, if you keep using that argument to n nodes, you have that was n minus 1 edges without having a cycle, which is the forest.
Okay, so you're imagining some process where maybe you're building a forest,
Yeah.
and then you were saying, oh, well, you can't add, and I think you said you need to somehow keep adding edges that go across components, right? Because
Edge where 1 endpoint is already in your forest and 1 endpoint is in your forest, and in order to like not create a cycle.
yeah, because you can't create a cycle, and so you're kind of keeping track. And now the details matter. We want to argue it's n minus 1 and not n and things like this. So I think you're also keeping track of maybe like how many vertices are out there implicitly and something like this. So I think that's what we're going to do, something along these lines, and we're just going to take a really simple. These aren't like hard to prove. I think it's just more like, what's a clean way to describe it that's very easy to read off. So, okay, that's exactly what I wrote. So imagine you're building a forest, okay? And all we're going to do is kind of do some counting along the way so that we reach this conclusion. So you start with an empty set, okay? And you're just going to add edges one at a time, right? So something like this. So somewhere in the middle, you have a forest and you're adding an edge, right? And somehow you want to say that you like terminate at n minus 1. So there is something written here. Anyone want to take a guess at it? It's not really, like the magic word is not induction this time, if I remember correctly. What do I kind of want to keep track of? So you're building a forest, you're adding one edge at a time, so they're never creating cycles.
Union set?
Sorry?
Union set?
Union sat.
No, like
Oh, union set.
union set.
Oh, so that's a data structure that maybe helps you implement this. But I want to just focus on the structure. Why? How come it doesn't get past n minus 1? I mean, you know it doesn't get past n minus 1, but why? I just want one sentence that really kind of nails it.
The nth edge would create a cycle
Why?
because a tree with n minus 1 edges has n nodes, and that's all the nodes of the tree. So you'd be adding an edge between the node and the tree and another node and the tree, and that would give you a cycle.
Yeah.
By pigeonhole?
By pigeonhole? Yeah, I don't know. That sounds nice, but I don't think so. Okay, so we say, oh, a tree. So I think maybe, okay, here's maybe one way to articulate it. So it is true, you will get to a tree. So you kind of notice some contradiction happening at the end. But how do you even know you get to a tree after n minus 1 edges and stuff like that, or something like this, right? So at some level, like, okay, let's take it really simple. Why don't you just keep track of the connected components in your graph, right? You start with empty graphs, there's n connected components because they don't touch each other. Now, if you add one edge and you connect 2 different connected components, what happens to the number of connected components? Yeah. Goes down by 1, exactly 1. Not more than 1, not less than 1. This is just like a slow counting argument. So it's going to go down by 1. And what does it start at? N. And what does it end at? 1. All right, so just keep track of connected components as you go. Then that'll make it really clear that you really add n minus 1, you get to a tree. You kind of knew this, but this is just one way to kind of articulate this cleanly. All right, so nothing too special. You all kind of knew this fact. Okay, we're just taking it slow. Okay, so that's 1. All right, let's do this other one. And I have in mind some kind of argument that's also kind of elementary and taking it slowly. Now you have a spanning set of edges, right? So now it's not just trees and stuff. So I have to think a little more. So the claim is that any spanning set of edges must have at least n minus 1 edges in it, which maybe is believable. But then the next question is like, what's a nice way to explain it? Yeah.
Can we not just reverse it, where we start with a disconnected set, but then we add 1? Maybe we have components that we add 1 until it's fully connected.
Okay, so if you kept adding edges until it's fully connected, you will end up at a spanning set. Oh, maybe that'll be fine. Yeah, okay, but we want to be a little careful. So if you start with an empty graph and you add edges, and then you'll need n minus 1 to get to one component, right? And you need one component to get to a spanning set. But that will show that some spanning set of edges has at least n minus 1. It doesn't quite tell you that every spanning set of edges has n minus 1. So I am imagining something that counts, but in fact, when you first said, like, can we do the opposite? I was even thinking like more opposite-y. That makes sense. Yeah.
If you maybe start by saying your spanning set takes every single edge of the entire graph, and slowly subtract off edges.
Yeah, so let's go back even more opposite with delete edges. Now we do want to be able to handle any spanning set. Of course, the complete edge set is spanning, but we want to say something about any spanning set, which is like a little bit more of an amorphous thing than a tree or forest to me, right? So let S be a spanning set, just any spanning set, right? Because I want to be able to address any spanning set. How many components are there kind of to start with? Not a trick question. Just one, right? Okay, spanning, so there's only one. The graph was connected to begin with, so there's only one. Okay, and now we're going to imagine removing one edge at a time. Something like this, right? Now, when I remove one edge, if I delete an edge, how much does number of connected components go up, or does it change? It goes up by 1. In fact, you should be a little careful. It goes up by at most 1. Because in fact, it could be a completely redundant edge, right? If you start with all the edges, you're removing edges, you might not make any progress for a while. But all that matters is that it goes up by at most 1. And of course, is there anything written down here? Yeah. So you start with one connected component. And when this process ends, you end up at how many connected components? N, right? So somehow you have this like ticker. It's going from 1 eventually to N. And when you click, it can only go up by 1. And sometimes it goes up by 0, right? So you're gonna have to click at least n minus 1 times to get from 1 to n. Okay, so that means I had to have n minus 1 edges. So again, but just taking it very simple, slowly. I think the only hard part about this is that like you might be tempted to try to write it in 1 sentence. And here all I did was write it in 3 or 4 instead, but keep it simple. Okay. Okay, so now we're just kind of putting some elementary observations together. You might find all this quite believable to begin with. Okay. So let me generalize this a little bit. We assumed last time that the graph was connected. What if it's not connected? There's like k connected components. There's like 3 different parts of the graph or something. Then the claim is that you're just going to kind of pop in the n minus 1 with n minus k. But why? It certainly pattern matches. It's like, 1 generalizes to k. It must be this. But, right? So the claim is that if the graph originally had k connected components, spanning set has to have at least n minus k. You can still have a spanning set because our definition of spanning is that it has to span every edge in the graph. So it doesn't have to actually connect the graph if the graph is disconnected. Yeah.
You substitute 1 in the previous arguments with k.
Yeah, so I think there's at least 2 ways to go about it. One is you can just redo everything. So if I was doing this argument, right, you start with n minus k. No, you have to be a little careful. Sorry. You still start with n disconnected components as you start with an empty forest, but you end at k. You don't quite get down to 1 because you can only get to k, right? So this will just become a k, right? So each time you can decrease it by 1, you go from n to k, you decrease n minus k times. And then here, if we revisit this argument, yeah, you start with k connected components, and you keep increasing, or decreasing, or sorry. You delete edges, but you increase the number of connected components until you get up to n. In the same kind of clicking analogy, you start at k, you get up to n, you have to click at least n minus k times. Okay? So that's one way to do it. I don't know if this is lazy or not, but it's like, okay, if I have k connected components, right? maybe there's 5 or something. This was like n1 vertices, n2 vertices, n3 vertices, n4, n5, right? And then you're going to get, n1 minus 1 edges here, n5 minus 1 edges here, n2 minus 1 edges here, n3 minus 1 here, n4 minus. So we just apply what we did for connected graphs to each of our connected components. So I just say, oh, this is a connected graph. I'll ignore everything else. And you'll get this, so whatever the n is minus 1. You put that all together, and all the n's, n1, n2, n3, that's going to give you n in the original graph. And you get minus 1 for every component, so you end up with minus k. Okay, so you can also apply the lemma to each connected component. Maybe that's easier, maybe that's not, I don't know. Okay, so, all right, so that's simple enough. All right, let's see what's written here. So again, we're just putting together little observations and getting a little practice, doing so in a clean, formally solid way. Okay, but they'll add up. We'll soon see why this is useful. So, all right, so here's some claims. Okay, or definitions, I'm sorry. So I'm gonna say that now we're gonna start thinking about maximal and maximum. Remember, our goal is to get a maximum size forest. But I first want to distinguish maximal from maximum. So I'll say a forest is maximal. I have a bunch of edges that forms a forest, and I can't add any more edges. Okay, so somehow it's like stuck. It's like locally maximal. I can't just add an edge anymore. And I want to distinguish that sharply from maximum, which really says of all the forests, this is the biggest possible size. Because there may be other forests out there that you can't just add things to, completely disjoint or something, right? So maximal just means kind of in a local way. You can't just directly add edges. And maximum means this is really the best one, no matter how you had gone about it. Truly the global maximum. And I should point out, computing a maximal forest is relatively easy. You just keep adding edges until you're stuck. You're stuck when it's maximal. Maximum is a global optimization problem. You might have a maximal forest and be like, is it the best? Right? You don't really know. And same thing for spanning. Okay? Minimal spanning set means I have a set of edges, it spans all the edges, and I can't delete any more without breaking one of these spanning requirements. Right? So it's just like minimal, maximal, or maximal, maximum. And a minimum is like the true opt. This is what we're really going after. Right? And again, it's very easy to find a minimal spanning set. I can start with all the edges and just drop things until I can't drop things anymore. But you don't know, is that really the optimum solution? Okay, so we see like a slight, I don't know if this problem is too simple. You've seen it before or anything, but this is always an interesting question for many problems, right? Minimal versus minimum, maximal versus maximum. Because minimal, maximal, you can often find that relatively easily. It was a greedy because it's almost like the algorithm is in the name. But what you really want is maximum and minimum. You want to actually solve a problem, right? And minimal, maximal is not necessarily going to cut it. Right? And I think when you start looking at these optimization problems, you need to start saying something about the difference between maximal and maximum, or if they're the same and things like this. Right? And it's really those observations you need to be able to, kind of in a principled manner, put together an algorithm. Okay, so that's the point I want to make this class. All right, so here's where we're going to try to put everything together. Okay, suppose I have a forest and a spanning set. Okay, and again, this is where we're going to try to analyze both problems jointly and come up with stronger conclusions than I could looking at either problem by itself. Okay, so the first claim is, if F is a maximal forest, then it's spanning. If F is a maximal forest, I can't add any more edges, then it's spanning. It spans all the edges. And the second claim is going to kind of be the opposite. If S is a minimal, not minimum, minimal spanning set, then it's a forest. Okay? So they're playing off of each other. Right? I'm really interested in getting a maximum forest, but for some reason I'm talking about maximal forest and spanning sets. Vice versa, I'm really interested in getting a minimum spanning set. But right now I'm relating minimal spanning sets to forests. Okay. Suppose this is true, why would it be useful? Yeah.
It provides structure to our focus.
It provides structure, but yes, but it lets you draw a very strong conclusion. Suppose you built the maximal forest, right? Because it's easy to do. You make some greedy thing. And say, this lemma tells you it's also spanning. Then you could say something very nice. Yeah.
You know that the maximal force is spanning, so it has to have n-1 edges.
Yeah. So now if we go back to kind of what we did, which again was, simple kind of counting arguments, right? We showed that any forest, its size, is bounded above by any spanning set. So if my forest is spanning, it's both less than equal to n-1, is greater than equal to n-1, is equal to n-1, if it's a connected graph. But also in general, like, I know I can't go any higher. Because any forest, its cardinality is bounded by any spanning set, right? And so once you kind of show that this forest has sort of the property of whatever the kind of dual problem is, so to speak, you've actually now certified that your maximal forest is a maximum forest. Yeah? So this actually gives you an optimality criterion. Right? Now you can actually argue, oh, my maximal forest is a maximum forest. But what's really helpful is playing off of this kind of opposite problem, sort of dual problem. Okay? And the same story applies to the second point. I know how to compute a minimal spanning set. I can just start with all the edges and just drop things until I can't drop things. But if I know that means it's a forest, and I can't go below any forest, right, just from simple counting stuff, then I have an optimum solution, right? And that means, okay, relatively simple algorithms will solve this problem for me, right? But the real key point is to look at sort of the other side of the coin for each of these problems, and it's how they play off of each other that sort of lets us justify, what's ultimately a nice, clean algorithm. Okay, so so those are these corollaries. It implies that a maximal forest is a globally maximum forest, and a minimal spanning set is a globally minimum spanning set. And we haven't really developed any algorithms yet, but now the algorithms are obvious. Just do something greedy. Okay, what really mattered was setting up the observations. So, okay. All right, so in both cases, they're going to be spanning forests with, if there's k connected components, n minus k edges. So that's where spanning tree comes in, is kind of where these two things meet. All right. Okay, so now let's prove this. And I should note, if you try to directly prove that a maximal forest is maximum, it's a little bit messy. Because then you have to compare it to a max. It's a mess. You'll see. This will be cleaner. So, all right. So now let's do this. I want to prove that if F is a maximal forest, then F is spanning. Anyone want to take a stab at it?
N is maximal forest, and it has n-1 edges. That means because there's no cycles, there's only one connected component across the entire graph.
So we don't know that a maximal forest, we have not shown that a maximal forest has n-1 edges. We show that any forest has at most n-1 edges thus far. Of course, I mean, that sort of is the conclusion we're going to get to, but I want to build up to it. Yeah.
Suppose the forest doesn't contain all n-1 edges.
Yeah. Okay, so here we can do, I don't know if we've done this much in this class, but we can do a proof by contradiction. Okay? So suppose F is a maximal forest but doesn't span everything, right? So let's say that F does not span some some edge E, right? So you have your forest. I guess it seems obvious if I draw it. And there's some edge that's not spanned, right? So it doesn't look like this. That's spanned. It has to look, something like this, right? So if we just go slowly and go through the definition of span, right? If F doesn't span E, it doesn't connect the endpoints of E, right? So that means if I add E to the graph, it won't create a cycle. If I created a cycle, then the remaining edges would have connected the endpoints of E. Okay, so spanning means it would create a cycle, and non-spanning means it wouldn't create a cycle. So yeah, you would just say something like, oh, then I don't know, by definition of span or something, F plus E does not have a cycle. So it's a forest. Whatever. And that's it. It's really just kind of going slowly through some definitions. Okay. So if it doesn't span, then the short story is you can add it. But if you just open up the definition of span, that means you're not already connecting the endpoints. So you can't be inducing a new cycle by adding this edge. Or you can do another contradiction thing. If you created a cycle, then the tree must have a path connecting the endpoints, in which case it spans E. So somewhere in there, there's a contradiction. Okay. All right, so yeah, so that's it. So you presuppose what if it was wrong, you reach some contradiction, so it must have been right. Okay, nice and simple. And that proves to you that, a maximal force is a maximum forest. All right, now let's just do the other one. And again, I feel like the spanning of side is always more awkward, so maybe it's a good exercise. Let's say I have a minimal spanning set. Okay. The claim is it must be a forest. Anyone want to take a stab at it? Yeah.
I guess you use like this thing. Idea, like
Sure.
so, like assume that S is a spanning set, or like I guess that's just a forest. Then if you take away edge, then you have a spanning set that's like with one less edge.
Yeah, so you should be able to take away an edge. But now, where is the edge? Let's pinpoint that edge. We want to say we take away an edge, but I want to go a little bit more precise there. So the suggestion is like, okay, suppose it's not a forest. And then if I remember correctly, you said, so we should be able to take away an edge and get a smaller set. So now let's figure out where the edge is.
It's not a forest, there's a circuit somewhere.
Yeah, there's a circuit, right? So S contains a circuit, right? Something that looks like this. And now you can say, look, if I remove any edge from that circuit, I remove this edge here, the rest of the circuit still connects the endpoints, right? And ultimately, that's going to still be spanning. If I'm worried about any other edge, and I originally had some path that used this edge, I can reroute it through the other side of this cycle, right? So maybe I'll go a little bit more slowly. Okay, so you have some kind of circuit. You say, I can get rid of this edge, right? You want to make sure it's still spanning. So, even if this was like used to span some other edge, right? I'm worried about that edge, and that's spanned by this circuit here, or path here, right? Well, okay, I can always reconnect around the circuit. Okay, so that's okay. These circuits represent redundant connections, so you can remove one and reroute around the other side. Okay, but relatively simple. But again, I think you just go slowly. So you should say S is not a forest because that pattern matches from before. And then what does that mean? It contains a cycle by definition. Again, the last one we just opened up the definition of spanning. This one we just opened up the definition of forest. So there's a cycle. There's my edge. So that we would look for. Like that's, I think, an important detail. Okay, so that's it. And why did I do this? Okay. So that's really the point, right? So so what we've shown is that what we really want to show algorithmically is that a maximal force, a maximum force, a minimal spanning set is a minimum spanning set. So we can solve both our problems. Okay, great. It's easy to write up an algorithm that's relatively efficient. You can use your disjoint set union, whatever you want. Okay. But I think the real takeaway is that we kind of identified these two opposite problems. They're actually dual to each other in the following sense. So at some level, like, okay, it's not as good, but we had one packing problem where I'm kind of trying to pack edges into cycles, and the other one is like I'm trying to connect edges and take a lot of edges and remove them. But more clearly, we just showed that any spanning set is bigger than any forest, right? So in that sense, you have this kind of direct opposition. They kind of bang into each other, right? And so ultimately, to try to show that like a greedy algorithm for maximal forest work, we didn't really directly show its maximum. We directly showed its spanning. That was easy to do. That was ultimately just like, oh, that's a definition of spanning. If it wasn't spanning, I find an edge, I can add it, right? It's fairly easy. And then that tells you its maximum. We kind of reached into this opposite problem. And then same on the spanning side, right? We didn't really directly show that a minimum spanning set is a minimum spanning set. It's a little awkward. Like, I have some solution, looks good. How do I know it's the globally best solution? But if you show it's a forest, that actually gives you like this lower bound, and you're meeting the lower bound. So you must have a best possible solution, right? So what we have is our first example of dual problems. They're like two sides of the same coin. And if I only looked at one of the problems, like you probably would have preferred maximal force, that seems very natural. The spanning probably seems a little more awkward. But if you looked at just one of those problems, it would have been a big mess if I had never invoked a word like spanning and things like this. It's only kind of from reaching over, looking at the opposite problem, kind of looking at them in a balanced way, an open way, that it becomes very clear. Okay, so our next lecture also is going to have this this idea of this duality. Two sides of the same coin. And it's by looking at the opposite side of the coin that you can say something about what you're originally interested in. Okay, so this is some, it's a little more sophisticated maybe in some ways than just doing induction or something like this. But it's, there's a lot of problems of this nature. Of course, we'll only do a few in this class. Okay, good. So that addresses cardinality. And now we're going to look at weight. Okay, which of course is probably a problem you've all seen before. Minimum weight spanning tree, maximum weight spanning tree, minimum weight set of spanning edges, maximum weight of minimum, whatever. And I'm going to make things simple and just assume all edge weights are distinct. Otherwise, you can break ties arbitrarily, alphabetically order them or something. And you can imagine that as like a very small decimal point or something to break ties. There's many ways to go about it, not a big deal. And but it will make some of our proofs a little bit simpler. And you can go back and think, oh, what if they're not distinct? And just work through ramifications. It's not such a big deal. Okay, so, right. So I think that in this class, it's going to be, I think you can pick like any combination. You also know that like as long as the weights are positive, which we'll assume, like a maximum forest should reach a spanning set and stuff like this. So we're basically always looking for spanning trees because there's no reason not to take more edges or less or whatever. So I think the notes are phrased as minimum weight spanning tree. You could have done maximum weight spanning tree and everything would be the exact same. You could have done minimum weight spanning set and you would arrive at a tree anyway. You could have done maximum weight forest and you would arrive at a spanning set anyway because you might as well take as much as possible. Right, so they're all kind of referring to the same thing, and I'll just talk about minimum weight spanning tree. Okay, which of course is the terminology you're probably used to. All right, and then what we're going to do again is I'm actually going to put off all the algorithms until the end. We're just going to like look at some structure about this problem. We're going to make some observations, and in fact, I'm going to present like all the algorithms all at once, and we're going to say, oh, they're basically the same up to some choice of data structure or something. Okay, but the correctness will basically be the same for all of them. Okay, so there's many ways to go about this, but what we're going to do is going to focus on something called good edges. Okay, and here's the idea. I'll say that an edge E, okay, is good if I look at any other set of edges that spans E. It could also include E. Oh, I guess doesn't include E is in the definition. Okay. And this has some weight. And the claim is that in any spanning set of edges, I can find some edge, with weight bigger than the weight of E. Okay. So any spanning set of edges in a graph, first of all, it's not clear how to check that something is good and things like this. There's some kind of computational questions that we're not worried about. This is just a mathematical definition. For any edge E, however I try to connect the endpoints, I'll find one bigger edge. And the edge weights are distinct, so there's no ties. So no matter how I connect the endpoints, I'll find a bigger edge. I'll call those good edges. Sometimes in literature, they're called safe edges. Like Jeff's notes call them safe edges. Okay. All right, so what's so special about these? Good edges? I don't know. All right, so now here's the claim. Okay, let me say okay, so what is this saying? Okay, so condition 2 is just saying E is good. And I just wrote out the definition again, so you don't even need to read it. So all I'm saying is that the following are equivalent for a edge E. E is good if and only if E is in every single minimum weight spanning tree. Okay, so these are edges that are safe to add to your spanning tree. They're in every minimum weight spanning tree. That's the claim. It looks complicated because I wrote out this definition, but that's just saying E is good. Okay, so that's the claim, and let's prove it. So I left this blank, hoping somebody will guess it. All right, so let's just prove this. Obviously, this could be helpful for making an algorithm because then good edges are natural candidates to try to add. So the claim is that suppose every minimum weight spanning tree contains E. Okay, the claim is that E must be good. So all you know is that every minimum weight spanning tree contains this particular edge. And now I'm saying that E must be good, which means no matter how you connect the endpoints of E, you'll find a bigger edge.
Proof by contradiction again.
Okay, so we'll try to do it by contradiction. So I'll say, suppose E is not good. There must be an issue. So suppose E is in every minimum weight spanning tree, but then it's not good.
There exists a set that spans E where the maximum edge is smaller than E.
Yeah, so E is not good. And that means you can find some way to connect the endpoints of E where every edge has smaller weight than E. Okay? Every edge in this tree. Because that's the definition. So where's our contradiction? Or like, what's one part we haven't used yet? There's only two parts. Yeah.
If that was true, then would spend it.
Yes, something to do with spanning tree. We haven't used that part, right? So E is in some spanning tree. There's minimum weight spanning trees, and maybe it overlaps a little with this set. Something like this or something, right? So there's some minimum weight spanning tree. Any minimum weight spanning tree contains E by assumption, right? So there's supposed to be some minimum weight spanning tree, but there's also some way to connect the endpoints of F where every edge is smaller than E. Okay, so now we certainly brought in both ingredients, part 1 and part 2, or the negative of part 2. And now we just got to find our contradiction. Yeah.
Question for definition of E being Is it that there exists a path that subtrahend?
Yeah, there exist, or the opposite. No. So the definition of good means for any way you connect E, at least one edge is worse. Which, if you go very slowly, if that's not true, that means there is some path connecting the endpoints of E where every edge is smaller. So the negation, like a couple bits flip in there. So this is just some path where every edge is smaller. And blue is presumably a minimum spanning tree, which must contain E. Using it, yeah. Okay, the red path is a minimum weight spanning tree, so let's be a little bit careful. It's still a path, but it doesn't span the whole graph. So it's not directly a minimum weight spanning tree, but I think it's kind of going in the right direction here. Yeah, a lot of this is like an exercise in vocabulary, but still. Yeah. Yeah, so if I delete this edge, right, it'll break the tree into two components. You know, as drawn, it'll be one component over here and one component over here or something, right? Because you have a tree minus one edge, now you have two components, okay? And all you know about this path is that it starts at the endpoints, one endpoint, and goes around, and it goes to the other end, and every edge is smaller. So there must be, here it's kind of drawn as to it, now I'll extend the tree a little bit, right? There must be some edge that goes across the two components. There could be more than one edge, because it could go like zigzagging across the components, but it has to be at least one, right? So as drawn, it'll be this edge here with a big arrow pointed to it, right? And all I know about this edge is that its weight is smaller. So I could delete E, insert any of one of these crossing edges, there's at least one, and that'll put a tree back together with n minus one edges, so it has to be a spanning tree and all that. But it puts spanning tree back together, and you just replace one heavier edge with a smaller weight edge. Okay, and that's your contradiction. So you shouldn't be able to improve the tree if it's a minimum weight spanning tree. Okay, so it's an exchange argument. That bad edge will give you an edge that lets you exchange and improve the spanning tree. You shouldn't be able to improve the spanning tree. Okay, simple enough. I don't know if it's simple, maybe I shouldn't say that, but still, it's done. All right, now we just need to go in the opposite direction. The claim is that if E is good, then it's in every minimum weight spanning tree. If E is good, it's in every minimum weight spanning tree. How should we start?
Suppose that's not true.
Okay, suppose it's not true. So I'm assuming E is good. So what does it mean for it not to be true? Let's expand out like the implications. If it's not true, then what? Yeah.
You've got some expanding that doesn't have E.
Yeah, so some MST T does not contain E. Okay, so there's some tree out there that's spanning, so it also spans E. And it doesn't contain, that's not fun. Maybe this is more interesting. It doesn't contain E. Okay, so that's your contradiction, right? Okay, if it's not true, there's some minimum weight spanning tree that doesn't contain E. Okay, all right. Now what? Yeah.
Since it's this spanning tree, like there has to be a path. So like one.
Yeah, so just keep working on definitions. It's a spanning tree, spanning in particular, so it contains some path containing the endpoints of E. Right? Okay, good. So we've used the word spanning. Now what?
Maximum of the edges along this path is greater than E.
Yeah, so now because E is good, and this is some path connecting the endpoints, there's some edge, I don't know, like this one, where the weight is bigger. Again, just that's what the definition says. If it's good, there's some edge that's bigger. Okay, and now what? Yeah.
Be better to remove that edge and put E in and get a smaller spanning tree. Spanning trees is not good.
Perfect. So if you like, see if I do this correctly. If you delete this edge, right, and you add it in E, you get back a tree again because it'll separate into two components, but then E still goes across those components. So you get back a tree. And meanwhile, you've subtracted W of F, you added W of E. W of F is bigger than W of E. So the weight went down. Yes.
WF has to be along this path. Because can't WF, because it's the max somewhere, can be like not in between 2 points.
Great point. So we did not actually, so you could invoke the good and good definition with the whole tree. Actually, we proceeded in 2 steps. First, I isolate the path in the tree that connects the endpoints of E. Okay. So because the tree spans E, there must be a path connecting them. And then I only apply my good definition to this path instead of the whole tree. It's actually a pretty interesting point. And that's why I was able to get an edge along the path in particular, is because I applied the definition to the path, not the whole tree.
Well, like just that path.
Oh, because it says I'm allowed to apply any set of edges that spans E. And this is just an example of some set of edges that spans E. The only requirement is that it spans E. And since it's connecting endpoints, that's the definition of span. So it's true, the whole tree also is a spanning set of edges, but it's more useful for us to kind of focus in on that path. Yeah, that's a good point. Okay. So you just set it up, you go through the definition slowly, you set up some contradiction. Yeah, maybe the hard part is getting the right definitions to work with to begin with, but I gave it to you. So from here, we just have to, I think, go slowly and surely and just sort these things out carefully. Okay, good. So now we have this like very strong characterization that every good edge is in every MST. So that at least suggests sort of like a generic MST style. I mean, to me, the obvious idea is like, let me just start with an empty set and just keep trying to add good edges. At least I know those are in the MST, right? So I can imagine some kind of like generic MST algorithm like this. I keep finding a good edge and I try to add it to T. Okay, and I can't go wrong because it's in every MST. Now, what's maybe one obvious risk in this algorithm? At least naively, if you didn't know all the algorithms already.
Adding a good edge might make the cycle possibly.
So you can't go wrong adding a good edge because it's in every MST. So that part's actually okay. Yeah. Yeah. First, how do you find a good edge? How do you know there is a good edge? Right? What if you run out of good edges? That's not clear here. So at some level, we need to see if we can find good edges. If you can find them reliably, then you always find one. Or we have to kind of scoping out the finding the good edge. So this is not really a full algorithm. Because obviously, like testing a good edge seems very non-trivial. Yeah, do I have to try every spanning set of edges around it? That's not so clear. Okay, so that's probably what this question is. Yeah, how do I identify good edges? And are there always good edges? Yes, exactly, perfect. Okay. All right, so here's a claim. Let me maybe draw it as a picture. So let's say you have some set of edges already. Okay, so if I've already picked some edges, they don't even have to be a forest, although for us they'll usually be a forest. Okay, this is some set of edges H. Okay, and I say, there's so many edges that are not spanned by this, right? There's many edges possible. Okay, and suppose like this one is the minimum weight edge of the unspanned edges. right? This is sort of the min weight edge of the unspanned edges. Okay? The claim is that this edge must be good. Right? So what does this give you? This is a certificate for good edges, right? Because at some level, if I gave you a good edge, and I said, well, can you prove to me it's good? It's a little bit unclear, right? How to come up with, how can you convince me that every other spanning set F doesn't have a smaller weight or whatever, because it's a quantified over all possible Fs. But this is giving you some situation. It says, look, if you have any partial set, H, and you find a minimum weight edge that's not spanned by them, then it's going to be a good edge. Then, that edge H says, E is safe. H is proof that E is good. Okay, so it's a certificate. You can reliably conclude, this edge is good because this H set of edges H, establishes it. So in that sense, it's a very strong claim. All right, so the question is, any ideas for how to prove it? Yeah.
Edge F and then are proof of good edges, right? So we can just see that the weight of F is always greater than weight of E, so we have to keep it.
Okay, so in other words, you're saying that all the blue edges can give us that big edge F. So yeah, okay. I guess I realize the definition is really small. Here's the definition of good again. Any path that connects the endpoints, I want to find one edge that's bigger. For some reason, I thought it'd be a good idea to put it on the side, but then I realized how comically small it is. So I think here's the key point. Look at any edge, any path that connects the endpoints. Something like this in this picture. All these colors look the same. Is there a different color? Okay. This is better. Something like this. It looks just as bad. But anyway, the point is, okay, that the red alone does not span your edge, because that's how, that's one quality of E, is that it's not spanned by your set of edges H. So if you have some other, path that spans E, it has to contain at least one edge that's not an H, because H alone cannot span E, because H does not span E, right? So there's got to be at least one edge that's here, this blue edge that's outlined in green. And then what do you know about that edge? And its relation to the weight of E. How do we choose E? Yeah. It's the smallest of all of these edges that are crossing H that's not spanned by H. So, okay, so there must be some other edge that's not spanned by H, and it's going to beat that edge. So that would give you kind of that edge that's bigger on the path, right? And you can do that for anything that spans E. Anything that spans E has to include one of the edges outside H, because H itself does not span E. And that edge will give you that bigger edge, and so that E is okay again. Okay? So this gives you some certificate to prove that an edge is good. Right? Which otherwise is kind of unclear. How I give you an edge, how can you prove to me it's a good edge? Okay. All right, so that's that. I realize maybe I should write more words, but it's okay. All right. So, okay. Let me start there. So now if I revisit the generic algorithm, right? And I want to start building edges. Now you can basically guess edges, right? In terms of this good edges and the certificate, right? Because now you kind of have a way to find good edges. So what I want to do is take this generic MST where at some level you want to keep adding good edges, but there's some ambiguity about how you find a good edge. And I want to fill it in using this lemma here. If I zoom out so the picture reminds you. All right. So how can I use this lemma that sort of certifies good edges to build some minimum weight spanning tree algorithm? And don't just give me the name of a famous minimum spanning tree, describe it from first principles. I also don't remember the names of the minimum weight spanning tree algorithms, so I wouldn't know what you're talking about anyway. I could probably remember, but anyway, yeah.
It's just like you can just take like the minimum weight edge that's not in like the current.
Okay, so can I just do like a greedy algorithm where I keep adding the minimum weight edge or something, right? Then I want to try to justify what would the h's be? Like the first iteration, you just have an empty set, right? And so what would h be? You want to justify adding the minimum weight edge. So if I just had some h that gives me the certificate, I'd be happy. What can h be? It's a trick question, yeah. Set of edges that don't span E. I'm not actually sure if that's even well defined because you need kind of many edges that work in concert to span an edge. So depending on which edges you take first, there could be many possible subsets of edges that don't span it because you're just like one edge away from connecting, I guess. So it depends on like the order. Yeah.
The null set.
Yeah, the empty set. When you're looking at the minimum, that first minimum weight edge, which you all instinctively know should be in the minimum weight spanning tree. What justifies it? Well, it's the minimum weight edge that's spanned by nothing because it's the smallest overall. So you could have applied it to H is empty and you would have been okay. So now you add the minimum weight edge to your graph. And now I guess you're thinking like, I just keep trying to find a next edge that's not spanned. So in round 2, I'm adding that second edge. What would be my H? Just that first edge, because your algorithm is literally finding the next unspanned edge, next unspanned minimum weight edge. And so whatever you've taken so far gives you your set H. Okay, and that certifies that each edge is good. So that's what we have here. Greedy algorithm apparently is known as Crusoe's algorithm. But you just sort the edges and you just add them one by one. It's maybe the most intuitive algorithm. Okay, and we'll come back to running time later because you can use some data structures to make some of the steps quicker. Like you want to figure out as I add an edge, try to add an edge. Is it already spanned or not? You probably already know the answer, but we'll come back to it later. Okay, first I just want to get some correct algorithms. Okay, so that's one idea. How else could you try building an MST? Yeah.
Edge. That's that node that connects to something. That's not where you get it.
Okay, so that is this. It's out of order, but that's okay. We'll skip this. All right, so this one looks a little bit like Dijkstra's algorithm. So what you suggested is I'll start at a vertex. I focus on a vertex, and I'll find a minimum weight edge that leaves that vertex. And then I'll find the minimum weight edge that leaves that vertex, what I have so far. And the minimum weight edge that leaves, the minimum weight edge that leaves, okay? But the key point is you only have one component, you're kind of growing it out. This is in contrast to the previous algorithm where you're taking edges all over the place. Okay? So I call it search because it feels like you're searching out from a vertex. Okay? Now, how can I justify it? What would be my set H? Even in the first one, right? The very first step, you're considering taking this edge that leaves this kind of starting vertex, right? So I need some set H that justifies taking that edge. Yeah. Sorry? Well, starting node is not a set of edges. Sorry? Well, this might not be the minimum weight edge overall. So, because the empty set will say, oh, you should take the minimum weight edge overall, because that would be the best one, right? But once you fix a starting point, this might not be the minimum weight edge overall. So H empty doesn't quite work. Yeah. Every edge not adjacent to the starting vertex. So I just I don't know, the rest of the graph, leaving out the starting vertex, right? And so the only edges that aren't spanned are, things that go like this, that connect your starting vertex to the rest of the graph. So I'm just going to take all the edges except for the neighborhood of my starting vertex. And that will let me just focus in on the edges leaving the start, and you took the minimum weight edge leaving the start. So H is everything kind of outside. Okay. Now what happens like partway through the algorithm? So, you've done this for like a few iterations. So any kind of arbitrary point in the middle. And now you're looking at all the edges that leave this component, right? You're looking at this edge and that edge. And the algorithm is going to take the minimum weight 1. Okay. And, so the question is, what's the set H that helps us justify? Yeah.
Is everything not in the name of everybody?
Yeah, it's the same idea, except kind of generalized to the set of vertices. So just everything on the outside that's not touching any of these vertices. Actually, not quite, because if it was this, then you would also be allowed to take these edges or something. They're also not spanned. So it does include everything on the outside, but we need a little bit more.
Plus, like, taken edges.
The taken edges. So I'll also include this. Okay, because if I didn't include that, then those previous edges are still kind of fair game for like that minimum weight edge, which we don't want. We want to try to justify taking a new edge that leaves the component. So I'll take everything kind of on the outside, not touching any of these vertices, plus the edges we've taken so far. And that will force you to pinpoint the best edge leaving. Okay, so that justifies that algorithm, this kind of search algorithm. You're always taking a good edge. Okay, let me go quickly then. One last strategy. This is almost the most practical algorithm. I'll make it quick. Okay, this is a parallel algorithm. And the idea is, in one iteration, you have a bunch of vertices, okay? And everybody picks their minimum weight edge, okay? And you have other vertices out there, something like this, okay? And you're going to do that in one round, and then you're going to contract the vertices, and then you're going to proceed. Okay, so it's like a parallel algorithm. Each round, every vertex chooses their best neighbors. And you can either think of them as components, and in the next round, every component chooses their best leaving edge. Or you can like think of shrinking the vertex, graph the component to a vertex, and repeating. Okay. And this again, actually, this is going to be the same thing as before. Each of these edges are good because you can do some, everything around it. Okay, so those are 3 algorithms. They're all good. Let's just briefly run through running times, which we've probably seen before. I'll make it quick. Okay, so greedy algorithm. The only tough part, right? Sorting the edges is easy. Now you're just going through edges one by one. You're trying to figure out, is this already connected in my graph? So you want something, you've probably seen this before, called disjoint union. Okay, so the idea is that you just start with like a bunch of singleton sets. In each iteration, you can check to see if 2 things are already connected, or you can connect them. You can merge them together. So you start with n independent sets, and then you gradually merge sets together. The sets represent the connected components. And there's an incredibly clever data structure that says that, look, if I start with n elements, and I kind of take m different unions, and at most, it gets down to 1 component, it's almost linear time. It's m plus n alpha n, which is the inverse Ackermann function, which is like the slowest growing natural function like ever. It's slower than log, it's slower than log. It grows slower than log, it grows slower than log log, it grows slower than log log log, however many logs you want, I think. So this is almost a constant for all practical purposes. Yeah, so this is always like a fun lecture. We could do it later, which is making data structures for disjoint union. There's like various tricks you can do. They get better and better and better until you reach inverse Ackermann. This is amortized. Okay. The parallel algorithm, what's there to say? So okay, so this is pretty quick. So each round, every vertex chooses its smallest neighboring edge. And then you contract and you repeat. So 2 things. In that first iteration, how long does it take? Sorry? Yeah, so you might think like, oh, each node needs to sort its edges to find the smallest one. But that's not true. To find the smallest, you can just scan through and find the smallest, right? So you don't have to sort them first. So that just takes OM time because you go through all the edges once, or once per endpoint. And then how many rounds do you need? Huh? V minus one. No, not quite. So in one round, everyone chooses a neighbor. So what happens to the number of connected components?
House.
It halves. So how many rounds do you need? Log n. So you just end up with m log n. This algorithm is actually maybe the most practical because it doesn't need any data structures. If you want to distribute it, it's immediate because every neighbor vertex looks at its own. You have to relabel to do the contraction, but that's kind of easy. Okay, so we're flying through this. And then lastly, you've probably seen this before. Prin's algorithm, I'm growing out the components, growing out the components, growing out the components. And what I want to do is like, oh, I have some component of 5 vertex. What's the next smallest edge, next smallest edge, next smallest edge, right? And what does that remind you a little bit of? An algorithm we've seen before? Dijkstra's algorithm, right? You're just trying to find sort of like the next vertex you're going to add to your component of minimum cost. Although for us, cost is a little different because I'm not adding up starting from S. It's just the edge of the next one, right? So if I can just keep track of each, so you can use Fibonacci heaps again, where you're just keeping track of each vertex. What's the cost, the best edge I've seen to get to that vertex from my component, okay? So the running time comes out to the same. This is going to take you some log n time. Okay, who cares? All right, so in summary, is this even correct? Oh, so the greedy algorithm, you're actually going to be bottlenecked by sorting the edges at the beginning. So it'll be m log n. The parallel will be m log n, just log n rounds of m time. And here you can do this Dijkstra style trick where you can use a Fibonacci heap to get that next vertex you add to your component. There's 3 MST algorithms. They're all basically the same, some slight variation on how you choose the good edges, but the structure is always the same. Okay, thank you.